Hi everyone, welcome back to my channel. Myself Arun Kashish. In this video, we are going to discuss some properties of modulus of a complex number and their use in solving problems. Modulus of z is square root of real part of z square plus imaginary part of z square. That is, z is equal to a plus iota b implies modulus of z is equal to square root of a square plus b square. Modulus of z square therefore is equal to a square plus b square. Now modulus of z conjugate is equal to modulus of z, as z conjugate is a minus iota b, so its mod is square root of a square plus minus b square, which is equal to b square. So square root of a square plus b square is modulus of z. One more important property is modulus of z square is equal to z conjugate, as z conjugate is a plus iota b times a minus iota b, which is equal to a square minus iota square b square, and minus iota square is plus 1, so we get a square plus b square, which is equal to mod z square. Next one is for complex number z1, z2, modulus of their product is equal to product of their moduli, that is modulus of z1 times modulus of z2. Similarly, modulus of z1 upon z2 is equal to modulus of numerator upon modulus of denominator. Now we extend this property to any n complex numbers to get these two properties. Now we use these properties to solve some problems. In the first problem, we are given a plus iota b and we want to show a square plus b square. Now a square plus b square, as we know, is mod of a plus iota b whole square. So we take mod on these two and then squaring, we get this as taking modulus and modulus of a plus iota b is equal to this square. Now this is equal to modulus of the numerator square, and this square is also comes outside, and then modulus of 2p minus iota square. Now what is mod of p plus iota square? It is p square plus 1 square whole square upon 2p minus iota square. Modulus is 2p square is 4p square plus minus 1 square is again 1. So we get the right hand side. Next problem. If z and omega are two different complex numbers with mod z is equal to 3, then find this modulus. Now again we use this property. Mod z square is equal to z conjugate. So mod z square is 9 is equal to z conjugate. Now we want to evaluate this modulus. So what we do, we put the value of 9 as z conjugate here. So we get this modulus as modulus of numerator upon modulus of denominator Now see, z is common in the denominator, so we take z common, and what we get, mod of z minus omega upon modulus of z times z conjugate minus omega conjugate mod. And since z conjugate minus omega conjugate is z minus omega whole conjugate, so we write this. Now this is equal to mod of z minus omega upon mod of z times mod of z minus omega conjugate. Now mod of z minus omega is equal to mod of z minus omega conjugate, so these two terms cancel out. We get 1 upon mod z, which is equal to 1 upon 3. So our answer is 1 upon 3. Next problem, let us see. Now see, this problem is almost similar to the previous one. Here we are given mod z is equal to 1. So mod of z square is 1 equals to z conjugate. Now we put z conjugate in terms of this one, and we write this modulus as modulus of the numerator upon modulus of denominator. Now this equals to modulus of numerator upon taking z common from the denominator, and we can write this as z conjugate minus omega conjugate whole conjugate, and then cancelling these two terms we get this as equal to 1 upon mod of z, which is 1 upon 1 equals to 1. Alright, next problem. In this we are given 4 different complex numbers with their moduli equal to 5 each. Now again, if we use this property, mod z square is equal to z conjugate for each of these 4 complex numbers, what we get z1 conjugate is equal to mod of z1 square, which is 25. This implies z1 conjugate is equal to 25 upon z, or z1 conjugate upon 25 is equal to 1 upon z1. That is 1 upon z1 is equal to z1 conjugate upon 25. Similarly, see, for all the other complex numbers, 1 upon z2 is z2 conjugate upon 25, and for the other 2 complex numbers also. Now we want to evaluate this. See, we can take 2 common from the numerator, so we get 2 times 1 upon z1 plus 1 upon z2 plus 1 upon z3 plus 1 upon z4 in modulus. Now 1 upon z1 is z1 conjugate upon 25, 1 upon z2 is z2 conjugate upon 25, and so on. So we can write it as 2 times z1 conjugate upon 25 plus z2 conjugate upon 25 plus z3 conjugate upon 25 plus z4 conjugate upon 25 in modulus. Now take 25 common, we get 2 upon 25 times z1 conjugate plus z2 conjugate plus z3 conjugate plus z4 conjugate, which is equal to z1 plus z2 plus z3 plus z4 whole conjugate using properties of conjugate. And now since mod of z conjugate is equal to mod of z, so this is equal to mod of z1 plus z2 plus z3 plus z4, which is equal to 8. So we get 2 upon 25 times 8, which is equal to 16 upon 25 as the answer of this problem. Next problem. Here z1, z2, z3 are different complex numbers with mod of z1 is 2, mod of z2 is 3, mod of z3 is 5. Now again we use mod z square is equal to z conjugate for the 3 complex numbers. We get z1 conjugate is equal to 4, z2 conjugate equals to mod z2 square, which is 9, and z3 conjugate square of 5 is 25. So now we are going to evaluate this. Here we replace this 4 by z1 conjugate, 9 by z2 conjugate, and similarly 25 by here z3 conjugate. Now see, z1 z2 z3 is common in each of the 3 terms. So taking z1 z2 z3 common, we get z1 conjugate plus z2 conjugate plus z3 conjugate. Now separating these modulus, mod of z1, mod of z2, mod of z3 times mod of z1 conjugate plus z2 conjugate plus z3 conjugate, which is equal to conjugate of z1 plus z2 plus z3. This equals to mod of z1 is 2, mod of z2 is 3, and mod of z3 is 5 times z1 plus z2 plus z3 modulus 5 cos mod of z is equal to mod of z conjugate. And now this value is given to be 6 in the question. So our answer is 6 into 5 into 6 is 180. In the next problem, we want to find mod of alpha minus 3 beta upon 3 minus alpha beta conjugate. Again, using mod z square is equal to z conjugate, for this expression, we have mod of this square is equal to alpha minus 3 beta upon 3 minus alpha beta conjugate times